Good evening, everyone. I'm Prithvish Chakraborty. I'm from Discovery Analytics Center. I'm not an author of the paper. Unfortunately, the first author couldn't come because of some travel issues, but this is a paper which is led by Discovery Analytics Center and done in collaboration with ARI and NEC Labs. So without further ado, I will just go into describing the paper and I will answer your questions on the way. So the problem here is finding anomalies in cyber-physical systems. And to give a brief idea of what a cyber-physical system can be, you can just look at something like a microgrid, where you have like multiple devices, some measuring like weather, some are like solar PV like detectors, and some maybe just like load balancers, and they're all connected in a microgrid. And typically, in its operation, you want to do two things. You want to first characterize the microgrid based on their associations, and then you want to sometimes find causes when something goes wrong. So that's what you can typically call an anomaly. And as the other talks led to the session, anomalies can be done at a single level, so it can be done at a univariate level. So you can just look at, let's say, the weather sensor and try to find out when it goes wrong. What's more interesting in the microgrid structure is when you try to find in correlated anomalies. So when typically, let's say, the relation between temperature sensor and humidity sensor are like different. So that's what this paper is about. So there are like two main parts in this paper. First is creating what is called a graph of invariants, and I will talk about a little later like what invariants are in these situations. But for just now, think of it's like something like a system description. And then based on this graph that you create in a training phase, you want to actually let it loose in a like next session to find out outliers and call them as anomalies. So invariants. So let's say you have two time series. So in the microgrid that I explained, it could be just like two sensors and they're spitting out their values. And just upfront, one of the assumptions or one of the key decision criteria in this paper was to align all time series. So if like a weather measures every 6 hours, then there is a PV system which measures like every second. You do a resampling of the system to get it all aligned in the same time. So there is no misalignment. So if such two time series, they like show the same relation over time or the entire time period, you call them as system invariants. So this time period is basically the training time period. And when after this training time period, you see that this relation is no longer holding for, let's say, even a single time point, you call that this relationship is broken, and you term them as a broken invariant. So let's look at the relationships that we are talking about, and let's dig a bit deeper into what are the different background works that are there. So on your extreme, like A, let's say that's A, extreme left, this kind of relation that's actually in there, and you want to find that. Typically, like most of the previous works, such as the ARX model, they would employ linear methods, and they would try to find out direct relationships. So for example, here x1, x2, and xn could be like three different sensors measuring three different quantities. And ARX could only find out the direct relationships. But what we're interested in is also find what we call as indirect relationships. So for example, in a system, there could be one single controller which is basically controlling both the syncing capabilities of a weather sensor and then a load balancer. And although load balancer and a weather sensor are not typically related, they're related through how the system is built. So there is some hidden layer in it. And so this hidden layer H1 to HK is what we want to enforce, or what we want to assume to find out more interesting features. And I will show you like two real data examples that we were able to find out. So to find those things, we applied something called a latent label. But before going into that, just let's look at the like the basic like the state of the art in this kind of a cyber physical systems that were done previously. It's based on what is called an ARX model, and it's very popular and it's very entrenched in the history of statistical time series models. You typically have two time series y, the target time series, and then you have x. And a point of mention, x could actually be a multivariate time series where these b's will then go to like vectors. So you have like typically two time series, and you regress y over itself over a period like w, like u, and then you regress it also over the associated values of x till like v, and there may be a lagged relationship between the two, so you employ that. And how it's used in this kind of a setting is that you try to predict for the value of y at time t using all the previous values of y till that point and the values of x, and then you take a difference between the y t and the y cap t, and if that error is like below some pre-specified threshold, you say that there is some relationship between these 2 points or these two signals at that time point t. To apply or to introduce the latent layer, the choice that were used by the authors was to use what's called a factor analysis. If you are like maybe like many of you here know what already factor analysis is, but just to give a brief idea why factor analysis and why not something like in PCA. In PCA, you generally rotate your axis or rotate your variables along the axis of the eigenvectors, and what's lost in that sense is that you lost a lot of interpretability of what you're getting. So in factor analysis is more like a generative model where you can have this h1 to hk, let's say there are like k factors that we're using here. And so you can have as a designer, you can have some control over the axis that you are trying to project the lowest subspace over. And if you have like multiple features, so here capital X involves all the different nodes that you are measuring, time series of all the different nodes that you're measuring. Just looking at the loading matrix, that can give you a basic idea of how the different nodes are connected together. And I'm going to give you a simple example of how we use this loading matrix to analyze into the system. So it has two parts to the thing. We first, over a mean shifted matrix of these different nodes, first you find the latent factors, and you typically, the choice of the factor, like the size of the factor k, you have like different rules for selecting that. It's in the paper, but I can illustrate it later if someone is interested. And then once you have found the factors, you basically go back to your simple ARX equation, and if you look at this equation, basically it's the same as the previous. So here you have the xj cap t, and then it's regressing over itself over a window u, and then it's regressing over another time series I over a window v with a lag l. But now you have this quantity which you actually, if you break it up, it's basically like a number of, if there are k factors, there is like k such beta t or bt into xit's. So each of these h are like different loading factors at particular times. And so it's a very simple model, and this also gives you a straight comparability with the previous ARX model. And you do the same thing. You take the difference between xj and xj cap t at any time point t, and if that is like less than a pre-specified threshold, you say there is some kind of relationships. So to construct the invariant graph, and this is where I'm introducing this invariance notion, you basically try to measure this error like throughout the time t, and then if at every time point t within the training period, two time series have some dependence, you call them a system invariant. To go a little bit technical about it, the way the errors are measured is based on something like a relative absolute error. So that's the EJI RAT. So you have the error at any time point t, and then you normalize it over the entire training sample. So TS and TE at the start and the end of the period. And since we are more interested in finding errors, kind of sounds bad because it's a criteria that we want to basically, if the error is small, we want to say it's a good thing. So we just transpose it to some accuracy matrix. So it's like a percentage accuracy, this FJIT, and so it's what we call the score. And so the definition of invariance is that if for all the time t's fjit is greater than some pre-specified threshold gamma, then we say that j and I are invariant. And you can see that that is equivalent to this minimum equation that we have, the simplified equation. So this kind of, till here we have not mentioned like what the algorithm could be. This can be anything. So xj cap t can be coming from either the ARX model, or it can be coming from our LFRX model, that's the latent factor model. And so there was a choice here when we were trying to find invariants from this microgrids, or like this in cyber physical systems, and to stop overfitting, and also to have a trade-off between, because LFRX is more costly to compute, there was a decision choice. And so what the authors did was that they first computed the score from ARX between two nodes, and if that is sufficiently high, so if that accuracy score is sufficiently high, you say that J and I are already connected by ARX. But if that's not sufficiently high, then you next compute the LFRX, and if that is higher than the pre-specified threshold, then you say it's okay. They're at least connected through the LFRX. So based on what we have done, so we can basically compute an invariance graph where two nodes are connected via an edge if the scores are higher, so if they are invariant. Once you have done that, then you want to actually detect anomalies, and to do that it's very simple. You actually compute this xj cap t and xj t for all the time points that you want, because right now you have a trained model where all the weights are known, and if that is greater than the threshold epsilon naught, which is by the way calculated based on previous work where people said that it's if it's 99.95%, if it's like more than 10% of the 99.5% confidence interval, it's fine. That's the error threshold that you want. And the other thing that you can do is that you can actually rank the time series by measuring the degrees, which degrees at the nodes in the graph when there was in the normal state and when there was an anomaly. And if there are like more changes, you say that there is more thing happening at that point. So we did like the authors did some analysis on some synthetic data. So you have like 8 time series, and they are connected according to various equations, where V8 is kind of interesting because if you look at it, it's a rectangular pulse, and then V1 to V2 they are somehow related, whereas V7 and V6 are related only between each other. And here you can actually see the loading matrix and the covariance structure between these points. And so we applied, the authors applied their algorithm on this thing, and on the middle panel you can see the graph that were recovered via ARX. Here you see the graph that were required by the new model, and this is the truth graph. And you can see for the normal condition, that is during the training period, our method were able to detect the graphs like much better with more accuracies than the ARX model. And what is the abnormal situation is what we were trying to simulate anomalies. And to do that, the authors systematically introduced Gaussian noise at one of the nodes. And you would expect once you introduce noise to this, that in the abnormal case, it should not be dependent with other nodes, and so the edges should drop out. And that's exactly what we see in the the recovered graph for new models as well as the ARX. But the key idea here to see is that the LFRX model is both able to characterize and detect anomalies here. The same thing could be applied or was applied to sensors in Berkeley Research Lab. There are 54 wireless sensors, and they were located all over the room. And the first thing, the base level analysis, what the authors did was to first do a factor analysis and then do a spectral clustering over the the k-means clustering over the loading matrix at size 6. And they could actually see that the loading matrix nicely clustered according to the spatial correlation, which is kind of interesting. And they also evaluated the results of using ARX and LFRX across just the ARX. And this is the error, that's xj cap t minus xj t. And they found that the error was significantly lower for most of these different sensors. And the LFRX plus ARX method was also able to identify more edges than the normal ARX model. So that's the way of like identifying. They were able to identify more invariants in the system. This is how it looks like. So here the pink lines are basically coming from the ARX models. So I mentioned that there is two steps. First you do through the ARX and then through the LFRX. And then the more interesting cases are found through this LFRX, the blue lines. So this is under the normal situation. But in an abnormal situation, you can see that there is a broken red line. So that is where the dependency was lost. And you can actually, and this was also one of the top ranked dependencies based on that degree metric that I mentioned. And you can if you look into that, this is really an anomaly. The same method was applied on a microgrid system, and that had like many like solar PV, battery, etc., etc. And there also the authors applied their methods on like and this is presented in terms of the type of devices they are, and you can again see that this method works better for both like intra-device edges and inter-device edges, and with better accuracy, and also and they're able to find more invariants. In terms of the anomalies, there are three plots and graphs in here. On the left, you can see it may not be too visible in this, but on the left you can see the normal situation. The middle one is when you actually turn on or off a device, and you can typically expect in those kind of situations that the correlations may change a little bit. And on the third one is when you can see that when you actually turn on or off a secondary load. And the authors actually found that the second situation gave rise to more anomalies than just turning on off like simple devices. So that was an interesting discovery from this. And these are some of the few examples from this microgrid, and the related anomalies, the top ranked ones are shown here, and you can actually see that they are really interesting anomalies. So to conclude, the authors found out through latent factor regressions more edges that are connected through hidden layers, and as well as they were able to identify anomalies in testing phases. So in future works, they aim to use this to other topologies like a mesh network, and they also want to use heuristic searches to reduce complexity.